So we're going to do our study, much as we do with electricity, we're going to move into something called the magnetic field. We'll describe the effect of magnets analogously to how we did charge. A magnet creates a zone of influence, a distortion in space, however you want to say it, which we call the magnetic field. And a different magnet placed in that field will feel the influence of the first. We'll talk about using magnetic dipoles, and we'll analogize it to electric dipoles. Remember, an electric dipole is a thing that has equal charge separated by some small distance, like plus here and a minus here. And we know that if we put the dipole in an electric field, the positives are pulled upward, the negatives are pulled downward. Since they're equal in size, they feel no net force, but they both feel a torque, which is clockwise in this case. So the whole dipole will rotate so as to align that the positive is in the direction that the electric field is pointing. So we're going to say the same sort of thing. We have magnetic dipoles, and so we're going to say if we have a compass or other dipole, we'll let it rotate until it stabilizes, and then the north will be pointing in the direction of the magnetic field at that point. Right? And that's how we'll define the direction of the field. We'll say it's the direction that a north compass points. Why do we use electric dipoles? Because there are no magnetic monopoles. So we can't do something like before we said, oh, let's see what the effect on a single charge is. The original way of defining the electric field, which was the force on a charge divided by that charge, doesn't work here because we don't have individual charges. So it turns out not to be an easy way to define otherwise, but this dipole analogy works perfectly, so we'll use that. By nearly universal convention, we denote the magnetic field as B. And you'll hear physicists call this not only magnetic field, sometimes they call it magnetic induction, which is a terrible name we're trying to move away from. And sometimes we'll just call it the B field. Why B? Historical accident. James Clerk Maxwell, who is a seminal figure in electrodynamics, who plays the role in electrodynamics that Newton played in mechanical dynamics. When he was laying out his major work, he listed the vectors he'd be using, and he started with A and moved on down, A, B, C, all the way to H. In modern notation, we only ever use A, B, and H, and we won't use, I think, either A or H in this course, so we're left only with B. And you might wonder, why didn't we call it M for magnetic field the way we have E for electric field? And honestly, it's probably just because of Maxwell. It's also because M is a pretty important figure, right? We use M for masses a lot, and it would be confusing to bring in a new thing called M. The units for B will have to wait until we've got a force law to compare it to. It doesn't make sense right now to say what are the units of B. We can talk about having a relative strength, stronger or not, and that would come down to how hard the torque was on those compasses. If we took two compasses, or put the compass in two different places where the B field was stronger, there'd be more torque. We'll often use iron filings to demonstrate the field around a magnet. Iron filing is literally just a piece of iron that's been filed down a bit, and we take all the small bits that have come off, and they will temporarily magnetize and then line up with the field. So they'll become tiny little magnets, and then they will, just like a compass, align with the field. And if we look at this particular experiment where they've put iron filings down under this magnet, probably under a clear plastic sheet or something, otherwise they'd all cluster around the magnet too. But if we look here, we can say, well, the magnetic fields are along where the lines have come out. And remember that the compass points in the direction of the field. So if I'm looking at this, we have the field here must point like that, and the field here points like that, and like that, and like that. And so your book alleges, and I suppose we agree, what this ends up showing is that field is leaving the North Pole and entering the South Pole. And that's a good thing to remember, that field leaves a magnet through its North Pole and enters the magnet through its. As with electric field, we can use either a map of field vectors as shown on the left, or a map of field lines as shown below. Field vectors just point the vector in the direction that the compass is pointing, and we, by convention, will start the dot of the vector, the end of the vector, at the middle of the compass. And the length of the vector would, of course, represent its strength, as usual. So we see stuff like this. Or in the slightly more abstract fashion, we can do field lines, where the direction of the B field at any point is tangent to the line, along the lines of how we had electric field, which pointed in the direction tangent to the field lines. They're closer together when the magnitude of B is greater. And every magnetic field line leaves the magnet at its North Pole and enters the magnet at its South Pole. We'll talk later on what's going on inside. Like this is what's happening outside the magnet, what's happening on the inside of the magnet. And we're going to defer that for the moment. So we're going to talk about the big book of field diagrams for magnets. There's just a few configurations whose fields are worth knowing. You can kind of figure out other ones, but these ones come up a lot. The most important, the one that you actually need to know sort of cold, is a single bar magnet. Your book gives it to you in both filmed far away, with so you can see what it looks like far away. And we get some field like this. And then they zoomed in a bit and show you it gets a little bit more complicated, but not crazy complicated towards the magnet itself. This is the clean figure you should be able to sketch or recognize. If we add two bar magnets who are aligned, north facing south and so on, then we get the field on the left. Here's the physical iron filings. This is sort of a sketch of that as just field lines. Notice that the north lines can leave the North Pole and go back to their own South Pole, but they can actually also go from north to the other South Pole. Right? There's no reason why the field line has to enter and leave the same magnet. If we have them opposed, so north facing north, then we get this figure. Notice there's very weak movement in here because these are not particularly aligned, right? They're just scattered, meaning there's not much of a field or maybe no field at all. And if we look at the picture, we get very sharp bending away so as to get to not cross into the North Pole. And much like electric field lines, it would make no sense for them to cross. So they must never ever cross, because then at that point, the compass wouldn't know which way to spin. One of those refrigerator magnets you buy has a more complicated and weird case where we have alternating north and south next to each other, and the field is almost entirely on the plane side. And the poles are ending being much like U-shaped magnets. And we can see the field here using a filing sheet, and we get very strong banding at these boundaries. The Earth, it turns out, is magnetic. We'll talk later about where magnetism comes from and why, but the Earth has a noticeable magnetic field, which is how we discovered all of this to begin with, because people noticed that the lodestones would point north. So at the root, I guess we all knew that. Since the north pole of a magnet is attracted to geographic north, that must be a magnetic south, which is a confusion of terms that we have, which is a bit of a shame. But the geographic north pole of the Earth must be a magnetic south pole because it attracts magnetic north poles. Also, it's not actually at the rotational geographic north pole. In other words, we have the Earth spinning. The line through the center of the Earth gives us the two poles. The Earth's magnetic pole is offset a bit. Right now, it's currently in northern Canada, and it wanders. So it drifts by a fair bit, actually, every year. I forget how much. But it wanders around a bit. So navigation in the Arctic and Antarctic is actually quite complicated because you can't entirely rely on your compass. You have to be a little bit more careful. It also is three-dimensional. We've been acting like everything's two-dimensional, but it's three-dimensional. So we find that near the two poles, the magnetic field is plunging into the Earth or coming out of the Earth and is nearly vertical, whereas near the equator, it is basically horizontal. And so you also always call it dip angle. How much does the compass want to deflect if you're holding it horizontally, how much does it want to dip into the vertical plane? And that's an important thing, again, for navigating. The planet Jupiter is a massive source of magnetic force. It has a very, very strong field. We'll talk later about strengths. This is from an article that claims it's actually quite complicated, that there are sort of several places where field seems to be coming out of Jupiter or actually going into Jupiter. And so it's sort of like a dipole, just like the Earth was sort of like a dipole, but not quite. It's a little bit more complicated. And the Sun itself is a huge magnet as well. And so the fields are, again, very complicated. Jupiter and the Sun are complicated in part because they're gaseous. And so there's not like the magnetism doesn't get fixed anywhere. And the Sun is even more complicated because of plasma. So it's a charged thing generating its own magnetic fields in response to the magnetic fields of everybody else. You can see places where there are these eruptions and holes in the Sun, and that's places where the magnetic fields have canceled in weird ways. You can also see this loop out here, which is one magnetic field line of the Sun, which plasma is shuttling along. You can see some others coming out here. So the sun is highly visual because its own structure follows the field lines on it. On the Earth, the field is really too weak for us to see it that way unless we get special with things like the iron filings. All right, so one little sort of test on this. A compass is placed next to a bar magnet as shown. Which figure shows the correct alignment of the compass once it's come to rest? So here I've reproduced the bar magnet field that we had before, and we can see that at that location, the field lines are pointing, they're pointing to the left, so the compass should line up pointing to the left, so our answer is A.